Welcome to Maths for You YouTube channel. A past question on complex algebra, complex numbers from Sri Lankan A-level past paper. Let Z, Z1, Z2 are complex numbers or element of complex. Show that number one, a real part of Z is less than or equal modulus Z. The second part is Z modulus of Z1 over Z2 equal modulus Z1 over modulus Z2. Z2 not equal 0. Let's start with that. So say let Z equal X plus Y is a standard format, and X, Y are real numbers or element of real. So module of Z is standard again is the property of complex. The modulus of Z equals square root of X squared plus Y squared. X squared, Y squared are positive. So X, Y are real, and X squared, Y squared are positive. Therefore, square root of X squared plus Y squared is greater than X because of square root of X squared plus Y squared. So it just is more than X. But if Y equals 0, then X squared has X equal square root of X squared plus Y squared. Y is 0. So square root of X squared is a X, therefore 0. Equal. So real part of that, which is X, that is less than or equal X squared plus Y squared. So the real part of Z is the modulus Z. That is the first part we have been asked to prove or show. Right, the next part is modulus of Z1 over Z2 equal modulus of Z1 over modulus of Z2. So we need to prove it. So let's say the polar format is easy to prove it. So I just took the polar form. There's another method. I just after this I'll show you. Z1 equal R1 is the modulus, and cos theta 1 plus I sine theta 1. Z2 equal R2 modulus, cos theta 2 plus I sine theta 2. So Z1 over Z2, simply divide one of the complex from other complex. It will give you another complex anyway. So R1 is Z1 is R1 time cos theta 1 plus I sine theta 1 divided by R2 cos theta 2 plus I sine theta 2. And this type of quotient function, what we do, we actually multiply the denominator, the conjugate of the denominator, top and bottom, multiplied by the conjugate of denominator. So R1 cos theta 1 plus I sine theta 1, the conjugate of denominator, just R2 is out, just the cos theta 2 I sine theta plus I sine theta 2 is a conjugate is cos theta 2 minus I sine theta 2 divided by R2 cos theta 2 plus I sine theta 2 times cos theta 2 plus minus I sine theta 2, the conjugate. The denominator, just R1 there, and cos times cos, cos theta 1 times cos theta 2, cos times sine I minus I sine theta 2 cos theta 1, and then I sine theta 1 cos theta 2 minus I squared, so minus I squared sine theta 1 sine theta 2 divided by the denominator is cos squared a plus b, a minus b. Therefore, cos squared theta 2 minus I squared sine squared theta 2. I squared is minus 1. Therefore, the nominator R1 cos theta 1 cos theta 2 plus sine, I just separate or rearranging it. So the reason I just put sine theta 1 sine theta 2 is this one. I is minus 1, so minus minus plus, so sine theta 1 sine theta 2. So rearranging it, I, if you take I out, sine theta 1 cos theta 2 minus cos theta 1 sine theta 2. Just do it to remind the trigonometry identity. So the trigonometry identity for the first one, cos, sine, sine. So the trigonometry identity, so cos A, cos B, plus sine A, sine B, that is equal cos A minus B. That is what we have it here. And then sine A cos B minus cos A sine B, that is equal sine A minus B. That is this one. So we just simplified it using the trigonometry property or trigonometry identities, so trigonometry formula. So if you do that, the denominator just R2, so R1 and R2, cos theta minus theta 1 minus theta 2 plus I sine theta. So if look at it, the right hand side, R1 and R2 is the modulus, and cos the theta 1 minus theta 2. So it's another complex. So just one in bracket is another complex. It's, I just call it ZY. So the modulus outside R1 and R2, ZY is the right hand side. Left hand side again is a complex. It's just, as I said, it's simply division. All the algebraic function is applicable to complex too. So just this is a complex, Z1 or Z2, it's complex because the right hand side has already been proved. So Zx, I just call it Zx. So Zx equal R1 and R2 Zy. So this is if you can see it, the right hand side. So two complex are equal. So it's Zx equal R1 and R2 as a modulus, and Zy because of that is in the form of polar form. So left hand side, the modulus is Z1 over Z2, and the right hand side is the modulus is R1 over R2. So Z1 over Z2 is R1 R2, but Z1, the modulus, just modulus Z1 is R1, Z modulus Z2 is R2. So the modulus of Z1 over Z2, we know R1 over R2, but R1 over R2 is Z1 over Z2, modulus Z1 over Z2. That is what we have been asked to prove. As I said, there's another way of doing it. I do not quite sure about this is applicable to Sri Lankan A-level syllabus. So I just giving it. So there's another format we can use. Z1 equal R1 e to the power of j theta 1, Z2 equal R2 e to the power of j theta 2. Z1 over Z2, so it's one complex divided by other complex, which is R1 over R2, e to the power, because of the power goes to the top, e to the power of j, theta 1, theta 2, j is common. And then Z1 over Z2 modulus is R1 over R2, because of that is the R1 R2 is modulus. So Z1 is R1, the modulus of Z1 is R1, modulus of Z2 R2, so modulus of Z1 over Z2 equal Z modulus of Z1 divided by modulus of Z2. So it's another way of proving it. This particular method may not be applicable to Sri Lankan A level, may not be in their syllabus to use this format. The first format, yes, is applicable. Right. Second part or third part or the next part, deduce that the real part of Z1 over Z1 plus Z2 less than equal modulus Z1 over modulus Z1 plus Z2. So the real part of Z1 over Z1 plus Z2 is, as I said, a complex. Z1 over Z1 plus complex, it's a complex. So it's just complex. As I said, the algebraic operation will keep the complex going. So the real part of whatever the complex come out of Z1 over Z1 plus Z2, real part is less than Z1 over Z1 plus Z2. Right. So the real part of Z1 over Z2, Z1 plus Z2, we have proven from the first part, the real part of a complex is the modulus of that complex, is less than or equal that particular modulus. So just real part of a complex number is less than or equal the modulus of that complex, which is Z1 over Z1 plus Z2 less than or equal modulus is Z1 over Z1 plus Z2. That's from the first part. And the second part says the modulus of Z1 over Z2, Z1 plus Z2, the whole thing equal separate. The denominator Z1 is the modulus of Z1 divided by Z1 over Z1 plus Z2. So that is again from the second part we proved it. Therefore, the real part of Z1 over Z1 plus Z2 is because we said it before in that we could call it one, we call it two. So from that one is the real part of Z1 over Z2. We know we said that less than Z1, the whole thing, this equation one. But the equation one, the right-hand side of the equation one, we proved it, or we said it from the second part, is separate the modulus of Z1 divided by the modulus of Z1 plus Z2. That's what. So the real part of Z1 over Z1 plus Z2 is less than or equal modulus Z1 divided by modulus Z1 plus Z2 is complex. So that is another part which we have been asked to prove. Yeah, that is this one. And again, verify that real part of Z1 over Z1 plus Z2 is 30, and the real part of Z2 plus Z1 over Z2, Z1 plus Z2 is equal 1. Right, okay, just verify. Okay. So as I said, it's the algebraic operation of complex to complex through complex, whatever. The result will be complex. So it's Z0. It just we don't need to worry about Z0. Whatever the operation on the right hand side, it gives you a single complex, which we call it Z0. So that is equal. We have to consider Z1 over Z1 plus Z2 plus Z2 over Z1 plus Z2. As I said, the algebraic operation will apply to complex. So the LCM is Z1 plus Z2. Therefore, denominator Z1 plus Z2. Z1 plus Z2 over Z1 plus, so the exact same complex on the denominator, same complex because of the Z1 plus Z2 is a complex, another complex. Z1 plus 2, another complex. So it's just same complex divided one by other will give us 1. So again, you can simply ask this one, is it complex? Yeah, it is complex, but there is no imaginary part. So 1 plus 0i, you can call it. Anyway, so Z1 plus, so this is Z1 plus, Z1 over Z1 plus Z2 plus Z2 over Z1 plus Z2 is equal 1, which we proved it. So there are two complexes here because Z1 over Z1 plus Z2, one complex, Z2 over Z1 plus Z2 is another complex. So there are two complexes, is one. So the two complex addition is give you another complex. But that is equal just the real part. So there is no imaginary part. So these two left-hand side complex add together gives a complex. That is equal just 1. So the left-hand side, the real part of left-hand side individually, the real part of Z1 over Z1 plus Z2, and the real part of Z2 over Z1 plus 2 is 1 because of these both sides are equal. So that's another part done. Okay, that's first part, all right. And show that the modulus Z1 plus Z2 less than or equal modulus Z1 plus modulus Z2. Right, okay, that is again more. Okay, we know from the first part of the our question, the real part of any complex is less than or equal the modulus of that particular complex. So real part of Z1 over Z1 plus Z2 is less than or equal the modulus of Z1 plus Z2. The same real part of Z2 over Z1 plus Z2 as a complex number, and is less than or equal modulus of that same complex Z2 over Z1 plus Z2. Then if you add them together, 1 plus 2, so the left-hand side, the real part of Z1 over Z2, real part of Z2 over Z1, which we have proved here, that is equal 1. This one equal 1. So the left-hand side, when you add it, it's 1. The right-hand side is modulus Z1 over Z1 plus Z2 plus Z2 over Z1 plus Z2. Z2, sorry, Z2. So if you could separate, okay. Then we know from that second part of the previous, previously, we proved it here, this one. If you look at number 2 here, Z1 over Z1 plus Z2 modulus equals Z1. So this is a quotient form of a complex. The complete modulus equal the denominator modulus divided by nominator modulus divided by denominator modulus. So that is, so we know Z1, the whole thing, Z1 over Z1 plus Z2 modulus plus modulus Z2 over Z1 plus Z2. We can separate it. The modulus Z1 divided by modulus Z1 plus Z2, modulus Z2 divided by modulus Z1 plus Z2. And then, of course, LCM, modulus Z1 plus Z2. Therefore, the nominator, modulus Z1 plus modulus Z2 divided by modulus Z1 plus Z2. So cross multiplication, even though it's less than or equal, cross multiplication, the modulus Z1 plus Z2 less than or equal modulus Z1 plus Z2. That is the last part we have been asked to prove. It's just a complex number. The algebraic operation is applies, and then any complex multiple, addition, subtraction, division gives you another new complex. So that is one, and the polar format we use to prove it. And the another method which I put it here, anyone want to take it, this is good. But if you want to ignore it, ignore it. So we have done the question. Thank you. Please subscribe the channel and share these contents with other A-level students. Thank you.